Hi everyone, today we're doing notes on 4.2 and 4.3, more with probability. So we have the multiplication rule. If your events are independent or mutually exclusive, we take the probability of A and B. That's equal to probability of A times probability of B. In general, if your events are dependent, the probability of A and B is equal to the probability of A times the probability of B given A, or the probability of B times the probability of A given B. The addition rule says if you have independent or mutually exclusive events, then probability of A or B is the probability of A plus the probability of B. In general, if you have dependent events, probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Conditional probability, the probability of A given B is the probability of A and B divided by the probability of B. And you can see with simple algebra that these are the same. If I multiply by the probability of B, we have that the probability of A and B is equal to the probability of A given B times the probability of B. All right, an example of independent events. Suppose you're going to throw 2 fair dice. What's the probability of getting a 5 on each die? So it's 1/6 on the first, 1/6 on the second. That's going to give us 1 out of 36. Andrew's 55. The probability that he will be alive in 10 years is 0.72. Ellen is 35, and the probability that she will be alive in 10 years is 0.92. Assuming that the lifespan of one will have no effect on the lifespan of the other, what is the probability they will both be alive in 10 years? Are these events dependent or independent? So it says the lifespan of one will have no effect on the lifespan of the other. So that means these are independent. So use the appropriate multiplication rule to find the probability that Andrew will be alive in 10 years and Ellen will be alive in 10 years. Please do this. So we can take 0.72 times 0.92, and that's going to give us 0.6624. An example of dependent events. Consider a collection of 6 balls that are identical except in color. There are 3 green balls, 2 blue balls, and 1 red ball. Compute the probability of drawing 2 green balls from the collection if the first ball is not replaced before the second ball is drawn. So we know that there are 6 balls in total, and there are 3 green. So the probability of pulling a green one first is 3 out of 6. Now the ball is not replaced, meaning now there are 2 green and only 5 in total. So we're going to multiply that with 2/5. This is going to give us 6 out of 30 or 1/5. All right. In general, a deck of cards. You draw 2 cards from a standard deck of 52 cards without replacing the first one before drawing the second. Are the outcomes on the 2 cards independent, and why? So this is no, they are dependent because you do not replace the card. We want to find the probability of getting a 3 on the first card and a 10 on the second. So 3 on the first card, there's 4 3s out of the 52 cards. 10 on the second. There are 4 10s. We didn't put the card back, though, so there's only 51 now. Multiply these. We get 16 out of 2,652, or 4 out of 663. Probability 10 on the first card and 3 on the second. So now, 4 10s out of 52 cards, times there's 4 3s. Again, we're not replacing that card, so there's 51. Again, this is 16 out of 2,652, or 4 out of 663. Find the probability of drawing a 10 and a 3 in either order. I want you to think about this one, and please do it. Okay, either order means it could be one or the other. So 4 out of 663 plus 4 out of 663 gives us 8 out of 663. An example of the addition rule for mutually exclusive events. Laura is playing Monopoly. On her next move, she needs to throw a sum bigger than 8 on the 2 dice in order to land on her own property and pass go. What is the probability that Laura will roll a sum bigger than 8? So we can look at the picture on the next page, and we want a sum larger than 8. So I'm going to highlight these. Larger than 8 means 9 or more. So here we have, this one is 9, 10, 11, 12. Here we have 9, 10, and 11, 9 and 10, and a sum of 9. So we see there's a total of 10 of these. So it's 10 out of 36, or 5 out of 18. The cost less clothing store carries remainder pairs of slacks. If you buy a pair of slacks in your regular waist size without trying them on, the probability that the waist will be too tight is 0.3, and the probability that it will be too loose is 0.1. Are the events too tight and too loose mutually exclusive? Yes, because pants cannot be both too tight and too loose in the waist. Okay, if you choose a pair of slacks at random in your regular waist size, what's the probability that the waist will be too tight or too loose? So we simply add these. 0.3 plus 0.1 equals 0.4. All right, addition rule with dependent events. Professor Jackson's in charge of a program to prepare people for a high school equivalency exam. Records show that 80% of the students need work in math, 70% need work in English, and 55% need work in both areas. So are the events needs math and needs English mutually exclusive? This is no, because we have these students here that need help in both areas. Okay, so use the appropriate formula to compute the probability that a student selected at random needs math or needs English. So we're going to take our math, we have 80, English is 70, and then 55 need both. So we're going to do 0.8 plus 0.7 minus 0.55, and that's going to give us 0.95. All right, employee type and political affiliation. I'm actually going to add lines here just to break off our total row and column to make it a little bit easier to see for us. Using the table, let's consider other probabilities regarding the types of employees at Hopewell and their political affiliation. We're looking at production worker and independent. And suppose an employee is selected at random from the group of 140. If we want the probability that someone is independent, that means we have, here's 17 independents out of our 140 total. If I want the probability that someone is a production worker, well, I can see there's 92 production workers out of our 140 total. All right, this time I want the probability that someone is independent given they are a production worker. So this is a conditional probability. We need to make sure we restrict our attention to production workers since that is the condition given. Again, this is the probability that someone is independent given they are a production worker. So whatever they're given, that becomes the total. I want you to find this, please. Okay, so our total is the production worker. So now this 92 becomes our total. And we want the probability that they're independent. So that's going to be this 8. So this is going to be 8 out of 92, or 2 out of 23. Our next question says, Compute the probability independent and a production worker. In this case, look at the entire sample space and the number of employees who are both independent and in production. Well, we know the ones that are independent and in production is this 8 out of the 140 of the grand total. So this is 8 out of 140, or 2 out of 35. All right, use the multiplication rule for dependent events to calculate the probability that someone is independent and a production worker. Is this the result the same as that of part? This should say 3, not C. All right, so let's check. I know that the multiplication rule says this is the probability of independent given production worker times the probability of a production worker. So independent given production worker is 2 out of 23 times probability of a production worker we had was 92 over 140. This also can reduce to, I'm going to reduce this now to 23 out of 35. And so then, if we multiply these together, those 23s cancel, and we get 2 out of 35, which does match number 3. Okay, now we need to compute the probability that someone was independent or a production worker. And then we're wondering if these are mutually exclusive. So the probability that someone is independent or a production worker, probability of independent plus probability of production worker minus the probability of independent and production worker. Okay, so probability of independent, this was 17 out of 140. Probability of production worker, I'm going to use the unsimplified one here. This was 92 out of 140. And then minus the probability that someone was independent and a production worker, which this is 8 out of 140. And therefore, that is going to give us 101 out of 140. Another way you can do this, if we look at our chart, we can also just take each of the individual parts. So we could take each of the independent. So we know that gives us 9 here and the 8. And each of our production workers, so that's 63, 21, and that 8, but we don't want to double count it. So we can also take those 4. So we have 63 plus 21 plus 9 plus 8 and divide that by 140. And that also gives us 101 out of 140. All right, now we want to look at conditional probability using the sample space. So we want the probability of getting a 5 on the first and a 5 on the second. So remember, we did this at the very beginning of our notes, and we did 1/6 times 1/6 and got 1 out of 36. But I'm going to show you how to do it looking at conditional probability. So probability of a 5 on the first. So that's going to be anything from this column. So that's 6 out of 36 in total, or 1/6. Probability of a 5 on the second, well, that's going to be anything in this row. So that's again going to be 6 out of 36, or 1/6. Probability of the second, given it happened on the first, well, if we look at that, that's going to be 1 out of the 6th, right? So again, given that it happened on the first, means that we're specifically looking at this column, right? Given it happened on the first, means we're only looking in this column. And so then probability it happened on the second also is this 1 out of those 6. Okay, so now probability on the first and second is the probability of second given first times probability of first is 1/6 times 1/6, which is 1 out of 36. Okay, we're also looking at 4-3 today. And we have our multiplication rule of counting. If A is the number of possible outcomes for event E and B is the number of possible outcomes for event F, the total number of possible outcomes for event E, then event F is E times F. So Jacqueline is in a nursing program and is required to take a course in psychology and one in anatomy and physiology, A and P, next semester. She also wants to take Spanish 2. If there are 2 sections of psychology, 2 of A and P, and 3 of Spanish 2, how many different class schedules can Jacqueline choose from? Assume that the times of sections do not conflict. So first we're going to make a tree diagram to show all of the possibilities. So first we have that there are 2 sections of psychology. So we have a P1 and a P2 for section 1 and 2. Then we have that there are 2 sections of A and P. So this is A and P1, A and P2, A and P1, A and P2. Last, there are 3 sections of Spanish 2. So from each of these, there are 3 possibilities. So Spanish 1, Spanish 2, Spanish 3, Spanish 1, Spanish 2, Spanish 3, Spanish 1, Spanish 2, Spanish 3, Spanish 1, Spanish 2, Spanish 3. I'm talking about the options, not the level here. All right, so if you're trying to read a tree diagram, for example, if I read along this branch here, that represents that I am taking the first section of psychology I am taking the second section of anatomy and physiology, and I'm taking the third section of Spanish 2. Okay? All right, now if I want the multiplication rule of counting, the counting principle, it says that the total number of possible outcomes for the event is we can multiply the outcomes. I want you to do that to get the total number of outcomes, please. All right, so we can take there are 2 psychology times 3 of A and P times 2 of Spanish 2. And that's going to give us 12 sections, which you can also see, or not sections, schedules, I'm sorry. And we can see that if I take the total here, this also comes out to give us 12 possible schedules of the different sections. All right, last thing remaining, permutations and combinations. So a permutation is the number of possible permutations of R items taken from N. The order of the arrangement matters. Combinations, the number of possible combinations of R items taken from N items. The order of the arrangement makes no difference. So the key words are the order does not matter. Okay, so we did an example of this last semester. When the order of the arrangement matters, think of the ice cream cone, right? So if here's our cone, if I'm eating ice cream, here are my 3 different flavors. In this case, you have to eat the red last, because if you eat the red first, the green and the blue will fall to the ground. So you would have to eat the blue, then eat the green, and then eat the red, right? A permutation, you have to eat it in that order, okay? A combination would be if I had a bowl of ice cream, and then here I have my red, green, and blue flavors. And again, in this case, it doesn't matter which one we eat first, right? It's in a bowl. It's all, nothing's going to happen. None of them are going to fall on the ground. They're all there, so the order does not matter, okay? So using these formulas for a permutation, example is P5, 2. That's the notation that this book uses. We did 5P2 last semester, which I'm going to keep up. Remember, this represents 5 factorial divided by 5 minus 2 factorial. This is going to be equal to 5 times 4 times 3 times 2 times 1 divided by 5 minus 2 is 3. So this is 3 times 2 times 1. The 3, 2, 1's canceled. This gives us 5 times 4, which is 20. Okay? So as a reminder, in your calculator, remember it's math, then PRB, the probability menu, and then you choose NPR. For a combination, our example is C93, or in other words, 9C3. So this is going to be 9 factorial divided by 9 minus 3 factorial, 3 factorial. So this is 9 times 8 times 7, 6, 5, 4, 3, 2, 1. Divided by 9 minus 3 is 6. So we have 6 times 5 times 4 times 3 times 2 times 1 times 3 factorial, 3 times 2 times 1. All right, so here we have 6 and below cancels. 3, 2, and 1. Well, I can reduce the 3 with 9, so this 9 becomes a 3. I can reduce 2 with 8, so my 8 becomes a 4. My 1 just cancels because dividing by 1 is the same. And so we have 3 times 4 times 7, which is going to give us 84. And as a reminder, in the calculator, this one is going to be math. Again, PRB, our probability menu. And now we're choosing NCR for a combination. All right, it says the board of directors at Belford Community Hospital has 12 members. 3 officers, president, vice president, and treasurer, must be elected from among the members. How many different slates of officers are possible? We'll view a slate of officers as a list of 3 people with the president listed first, the vice president listed second, and the treasurer listed third. For example, if Mr. Acosta, Ms. Hill, and Mr. Smith wish to be on a slate together, there are several different slates possible depending on the person listed for each office. Not only are we asking for the number of different groups of 3 names for a slate, we are also concerned about order. B says 3 members from the group of 12 on the board of directors at Belford Community Hospital will be selected to go to a convention, all expenses paid in Hawaii. How many different groups of 3 are there? I want you to do both A and B, decide which one's a permutation, which one's a combination, and calculate these, please. Okay, for A, this one is going to be a permutation. Okay, this is because the order on the slate makes a difference. Our N is 12 and our R is 3 because there are 12 people and we're choosing 3 of them. So we have NPR we're going to use. So 12P3. So if we use our formula, it's going to be 12 factorial divided by 12 minus 3 factorial. And that's going to come out to give us 1,320. Next, B, this one is a combination. So combination, our N is going to be 12. And again, 3 are getting chosen to go. So our R is 3. So now we're using NCR, which is 12C3. So 12 factorial divided by 12 minus 3 factorial times 3 factorial. And this is going to give us 220. And that's the end of our notes.